So we're going to do a lesson today with regards to chemical bonding. And we may have heard of this term before. What exactly does chemical bonding mean? Well, in this case, it's why atoms form bonds with other atoms. So how do we get compounds? Now, the whole purpose behind chemical bonding is that atoms want to become stable. And what do we mean by stable? If we know that we were talking about the Bohr-Rutherford at the previous lesson, and we saw that there were several atoms or elements in the periodic table that when we looked at their valence electrons, they had less than 8. So the goal of all atoms, in order to become stable, is they want to satisfy something called the octet rule, which in other words is to be able to achieve 8 valence electrons. That is what they want. They want to have 8 valence electrons. And as we drew different Bohr-Rutherford diagrams, we saw that there are many elements that do not have 8 valence electrons. So in order to get to that stage, or to be stable and have 8 valence electrons, they need to react with other elements, forming chemical bonds, and therefore becoming stable with 8 valence electrons. So how do atoms bond with each other? One way is by transfer of electrons. So that's the first one that we're going to be talking about, is the ionic bond. So the first type is called the ionic bond, and this is formed by the transfer of electrons from a metal, so it has to be in this way, from a metal to a non-metal. Okay, now we know that most of our metals are on the left-hand side of the periodic table and our non-metals are on the right-hand side of the periodic table. Now, when a metal and a non-metal react, we end up with something called an ionic compound. That's why we call it an ionic bond. And this ionic compound is held together with the ionic bond. It's what keeps the metal and the non-metal together. So an ionic compound is made of a metal and a non-metal. When a metal gives the non-metal electrons, it forms an ionic bond between the two elements. Now, when an element gives up electrons or gains electrons, it becomes an ion. So it's no longer an atom anymore. So I want to just do one example with you, and I want to look at sodium. Okay, now sodium is in group 1. And if you look at sodium, it has an atomic number of 11 and an atomic mass of 23. Now, because sodium is in group 1, and if you remember the trick from my previous video, if it's in group 1, that means it has 1 valence electron. So here's sodium sitting pretty, but it has 1 valence electron, and we just said that all elements want 8 valence electrons. So I want you to think of this question energy-wise. What's easier for sodium? In order to get a full shell, it can either gain 7 electrons, so that it would have 8, so then it would have 8 valence electrons, or it could just lose 1 electron, and by losing just 1 electron, it is then going to only have 2 shells. And I'm going to show you this using a diagram. So let's draw the Bohr-Rutherford. Actually, not exactly the Bohr-Rutherford. I'm going to do a simplified. I'm not going to worry too much about the nucleus right now. Here's sodium. We know that sodium has its first shell, and that first shell is going to hold our 2 electrons. Because remember, we have 11 electrons that we have to place here. So here's shell number 2. And that one is going to hold 8 electrons. I'm just doing it this way because I know it's full. And then we have our third shell. Oh, it's so hard to freehand this. There we go. It's a little wiggly, but there it is. Okay, so there's sodium. And we could just double check, count how many electrons we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that is how many electrons a neutral sodium atom has. So this is the atom. Now, we just said that in order for it to have a full valence shell, sodium had 2 options. It either had to gain 7 electrons so that the third shell would be full, or it could just lose its valence electron, leaving it with a full second shell. Well, it makes sense that sodium is going to choose the easiest, and it is going to lose 1 electron. And we'll talk about where this electron goes in a bit. Now, when it loses this 1 electron, sodium is no longer neutral. Because remember, we said that the atom is neutral because it has 11 electrons and 11 protons. But now that it lost an electron, we no longer have those numbers. So let's draw what it would look like. Well, here's sodium. It still has its first shell. It still has its second shell. But what I want you to notice is that its third shell is now gone. And the reason it's gone is because that electron that was in the third shell has left. It's gone somewhere else. So that's why we're going to draw sodium now like this without the third shell, because that electron went. Now, how many protons and how many electrons do we have? Well, here we have still 11 protons. That hasn't changed. Protons don't move. But now we only have 10 electrons. So remember, electrons are negatively charged, protons are positively charged. So if I have 10 negative charges and 11 positive charges, the total charge of this is now going to be +1. Because again, 10 negative, 11 positive, you have sodium, and here it's no longer an atom. We call it the sodium ion, because now it has a charge. And the way that we would write it is Na +1. It's sodium with a +1 charge, showing the person reading it that we no longer have a neutral sodium atom. We now have a sodium ion with a +1 charge. And that's how you would draw it, indicating that it has a +1 charge. Because look at its second shell now. Its second shell has 8 electrons. That's what it wants. It wants a full valence shell. And that is what sodium has now achieved. It achieved its full valence shell, so it is stable, and we have a sodium ion. But where did this electron go? Okay, so we said that sodium loses an electron. But where does this electron go? Well, this is where we now talk about the nonmetals. Let's look at chlorine. Okay, it's a favorite of mine because it's one of the most commonly used elements. So let's look at chlorine. And if you look at your periodic table, you'll see that chlorine has an atomic number of 17 and an atomic mass of 35. So when we are looking at drawing the Bohr-Rutherford for chlorine, what you'll end up doing, and I'm not going to go through the whole process of it, but if you were to draw all its shells, you would have, so here's chlorine, you'd have 1, 2, now I already know this because I know the chlorine Bohr-Rutherford, so I'm going straight ahead to draw that. So we need 17 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have to go to the third shell. 11, 12, 13, 14, 15, 16, 17. Stop. There's our 17 electrons. Okay, so there's my 17 electrons. I have a neutral chlorine atom with 17 protons, 17 electrons. We don't have to worry about the neutrons now because we're not discussing the nucleus. So what is chlorine going to do? What is a nonmetal now going to do in order to satisfy the full valence shell? Well, chlorine has 3 shells. Let's look at the outermost shell, shell number 3. It has 7 electrons. We know the third shell can carry 8 electrons. So that means that in order to achieve a full shell, chlorine has 2 options. First option is to lose all 7 electrons, so it'll have a full second shell. Or it can gain 1 electron and have a full third shell. And we know that atoms are always going to choose the path of least resistance, the easiest method. So instead of losing 7, chlorine is going to gain 1 electron. It is going to find an electron in order to fill its third shell. Now I'm just going to draw that extra electron. So it's going to gain an electron. So there's going to be an electron out there somewhere. Okay, there's an electron out there somewhere, and chlorine is going to gain it. So what's going to happen? What's chlorine going to look like after it gains that electron? Well, the nucleus stays the same. Shell number 1, shell number 2, and I still have shell number 3 here because it's going to have electrons in it. Nothing happens to shell number 1. That still has 2. Shell number 2 still has 8 electrons. Shell number 3 has the original 7 that were there to begin with. But now, I'm just using different colors so that you can see it. It has that 1 extra electron that it got from somewhere else. Let's look at see if it's neutral. Well, we know that it has 17 protons, but now instead of 17 electrons, it has 18 electrons. So 17 positive, 18 negative, because electrons are negative, we now have a net negative 1 charge. And this is our chlorine ion. And we would draw it as Cl negative 1 to show that we no longer are dealing with a neutral chlorine atom. We are dealing with the chlorine ion that has a negative 1 charge.